Okay, and those cyclic structures are called Hayworth structures. There's Fisher projection, Hayworth, and this is usually the way it's projected. Now, it's sort of three-dimensional, sort of not. The thick lines are coming out towards you, and then the thin lines are in the plane of the page. So you can think of it as kind of slanted a little bit. That's the anomeric carbon. And the anomeric carbon, remember, we can do alpha and beta. Alpha's down, beta's up. All the other configurations have to be either up or down for that specific sugar. For example, galactose has to have carbons 2, 3, and 4 the way they are. Down, up, up. Otherwise, it's not galactose. Glucose, for example, has got the carbon number 4 hydroxyl group going downward. And glucose goes down, up, down, up. That's a nice one because that's the most common monosaccharide out there. Carbon number 1, again, is the anomeric carbon. That's the one that'll open up to either an aldehyde or a ketone. Now, if it's fructose, it's carbon number 2. We're going to have a fructose structure coming up here in a minute. Okay, now, this is a big deal. All the cyclic structures can open up. The cyclic structures are more stable, so they spend more time in the cyclic form than in the open form. However, in the open form exposes an aldehyde or a ketone. Most of the time it exposes an aldehyde, but sometimes it's a ketone. So this is really important to understand because once the aldehyde is exposed, then it can undergo aldehyde reactions. So if we look at glucose here, notice well, carbon number 1 can be up or down. Ignoring that, we go down, down, up, down for glucose, okay? All right. Now, when we look at this glucose structure, it's got a hemiacetal present. And we know that because we have OCO. So that's yes. Number 2 is a hydroxyl group on the anomeric carbon. This is the anomeric carbon, and that OH group is on there. And number 3, is there a hydrogen there? And yes, there is a hydrogen there. So that is a hemiacetal. Now, hemiacetals are really important with carbs because it opens up to an aldehyde. When it opens up to an aldehyde, then all the aldehyde reactions can go, including oxidation. So when we do our lab on carbohydrates in a few weeks, we're going to be doing that. We're doing the Benedict's reaction. We won't be doing Tollens. I'm not sure why, but it's not in the lab schedule. But anyway, and that's what we're going to be taking advantage of is when that opens up, we have the aldehyde possibility of being oxidized. So when that opens up, this is the aldehyde it forms right here. So now if we expose this to an oxidizing agent, it can then oxidize to the acid. And notice also, this is a dynamic process. It opens, closes, opens, closes. And again, the cyclic one is more stable than the open one. And the reason, can anyone think of a reason why the aldehyde would be, the open one exposed to the aldehyde would be less stable than the cyclic one? Yeah, aldehydes are very unstable. So as soon as you form the hemiacetal, it becomes more stable. That's why the cyclic one's more common. So if we redrew these double arrows, and only be a little arrow going over to the hemiacetal, opening up. Okay, there are two main kinds of rings we're going to see in carbohydrates. And they're called heterocyclic. And hetero meaning the cyclic ring has got something other than carbons. Okay, we'll see this when we get into the nitrogens as well. Lots of heterocyclic rings have nitrogen in it. Very, very common in biological molecules. Okay, six-membered ring is a pyranose. And the five-membered ring is a furanose. And we always draw the anomeric carbon. I should say most of the time we draw the anomeric carbon to the right. Not always, though. Sometimes if you have a sugar that's bound up in a large molecule, sometimes they draw the sugar, the anomeric carbon, on the left side. But most of the time it's on the right side. And it's also labeled carbon number 1 with a hexose. That means glucose, galactose, are the two hexoses you're going to need to know. Those are both, carbon number 1 is the anomeric carbon. Okay. Now, fructose is different. Fructose is a furanose, 5-membered ring, and its anomeric carbon is carbon number 2. Still a hexose, but instead of 6-membered ring, it's a 5-membered ring. So on carbon number 2, that's the one that can be alpha or beta. So again, when it goes down, it's alpha. When it goes up, it's beta. Now, when this opens up, instead of exposing an aldehyde, it exposes a ketone. So now any ketone reactions can be undertaken. Now there's something that's kind of weird about fructose. And fructose, even though it's a ketose, can act like an aldose because of one exception to the fructose structure. So if we look at this guy here, That's a total line drawing. So when that opens up, it's like that. Now, and of course, this is a ketone here. If a carbonyl group is next to a hydroxyl group, they can swap places. So here we have a carbon next to the carbonyl group with a hydroxide on it. That means those two can swap. It's called a enol, as it goes through an alkene. So this is what it ends up looking like. Oops, see, you do this right. So the OH and the carbonyl group can swap back and forth. Now, this is the aldehyde. So fructose, even though it forms a ketone or a hemiketal, it can still undergo aldehyde reactions because of that hydroxyl group is right next to the carbonyl group. So that means ketoses can be oxidized, just like hexoses can be oxidized. I mean, aldoses. And then also, the anomeric carbon becomes carbon number 1 also. So this goes carbon number 2, oops. Okay. Okay, so any sugar that can be oxidized, we call that a reducing sugar. Okay. Because it forces, if something is oxidized, something else has to be reduced. Now, this statement here, all monosaccharides are reducing sugars. Even the ketoses, because the ketoses can convert to an aldehyde, with that one exception I showed you. All right. any of the hydroxyl groups on sugars can act like alcohols. So that means they can undergo alcohol reactions. And our next unit is on organic acids, and they form something called an ester, which is an acid and an alcohol together. So if we take phosphoric acid, it can react with any of the alcohols on there, any of the hydroxyl groups. Now, these are particularly important biologically. For example, DNA and RNA are chained together with phosphoric acid ester groups and a sugar, ribose. And the hydroxyl group on the ribose is what's undergoing that acid alcohol reaction. Now, as we mentioned before, so if we have an aldehyde plus an alcohol, it forms a hemiacetal. If there are alcohols around, it'll continue on to form a full-blown acetal. Now that's what is the essence of carbohydrate chemistry, is you have a monosaccharide that's got a hemiacetal in it. And we've got other monosaccharides around with alcohol groups on it. So when they link up together, they form a full-blown acetal. And that's how they link up. It's called a glycosylic linkage. So that's what they're talking about here. So let me show you. Okay, glycosides, which are hooked up molecules that have an acetal linkage, according to the statement, are not reducing sugars. There's a number of exceptions I'm going to talk about. In fact, there's a lot of exceptions. Also, all of you have heard about RNA versus DNA. The difference is the ribose sugar on the DNA is losing one hydroxyl group. So it's on carbon number 2. And because it's an anomeric carbon there, you can have alpha or beta. That means it's a chiral carbon. So if we look at the sugars I want you to know, the main one, the most important one, is obviously glucose. Glucose is the basis for tons and tons of reactions. Is anyone in here diabetic? Well, if you're a diabetic, whenever you get your blood tested, they do something called an A1C test. And that is a test. They also check your blood from a prick on your finger. But the A1C test determines how much glucose is stuck to your blood cells. The more glucose stuck to your blood cells, the more you have problems with too much sugar. And the sugar is glucose. So glucose is like all over the place. And obviously there are two versions, because in the anomeric carbon number 1, it can be up beta, down alpha. Frequently, when you have a food listing, they won't say glucose, they'll say dextrose. Most people don't know what dextrose is, so they're trying to hide the fact there's sugar in that product. But dextrose, glucose, same thing. It is not used very much as a sweetener anymore. High fructose corn syrup is used 99.9% of the time, or sucrose is used 99% of the time. Rarely glucose is. Glucose isn't very sweet. That's why I don't like to use it. Okay, so the way I like to remember this is glucose. If you remember the beta version of glucose, it alternates up, down, up, down, up. And the other sugar you need to know, other monosaccharide you need to know, is galactose. And the only difference between glucose and galactose is carbon number 4. Galactose goes up, glucose goes down. It's carbon number 4. Galactose is also a reducing sugar because it's got a hemiacetal in it. We have OCO. Hydroxyl group is there. And there is a hydrogen there. And you would know it's a hemiacetal because it's exactly the same as the right side of glucose. Most of you have heard of lactose. Lactose is a disaccharide, and it's a saccharide of galactose plus glucose is lactose. Lactose is also important for neurological reasons. All right, the third monosaccharide is fructose. And it differs because it's a ketose. So when it opened up, the first thing it does is expose its ketone, which can be converted to an aldehyde. So it's a combination of a ketose aldose. And aldoses can be converted to ketosis using the same mechanism. Okay. I haven't seen levulose used very much in food labeling. Fruit sugar, everyone thinks because it comes from fruit, it's healthy for you. No, the reason why fruit is healthy for you because of the fiber in fruit, along with a ton of other vitamins, where fructose by itself is just plain old sweet. Okay, so those are the 3 monosaccharides you need to know. Okay, you need to know some disaccharides as well. Now, disaccharides are formed from a hemiacetal and an alcohol, or full-blown acetal. So here we have the semiacetal, and we have the alcohol here, carbon number 4. Carbon number 4 is the least sterically hindered part of that glucose molecule. So usually carbon number 4 is the one that hooks up. The second least hindered one is carbon number 6, the one up above. And we're going to see that one's important. We start linking up things like glycogen when we get into the polysaccharides. Okay, so the glycosylic linkages are these guys here. Okay, so we have a So we've got the hemiacetal around the anomeric carbon number 1. And we're looking at carbon number 4's hydroxyl group as the alcohol. So when those two hook up, we get a glycosylic linkage. Now, the glycosylic linkages are labeled as to what carbons you're using to hook them up with. So this is a 1,4 glycosylic linkage, and also it is a alpha 1,4 glycosylic linkage because we're using the alpha form of glucose. And we can also, if we were using the beta form, it would be a beta 1,4 glycosylic linkage. But maltose, 2 glucoses together, is only an alpha 1,4 glycosylic linkage. No exceptions. It's a beta 1,4, it's not maltose. It's very, very specific. They discovered maltose in beer, hence its name, maltose. Now, the question is, I will always ask you these questions on tests. Is this a reducing sugar? Yes or no? And you need to be able to defend either it's a yes or no. So remember, we were talking about reducing sugars. What has to be in the reducing sugar for it to be a reducing sugar? Anyone remember? Yeah. It can be oxidized. Exactly. And how does it become oxidized? You're actually correct. But how does it become oxidized? It opens up and exposes. Exactly. It opens up and exposes the aldehydes, and aldehydes can easily be oxidized. Hence, it's reducing sugar. So we need to find the hemiacetal if it's a reducing sugar. So do we have a hemiacetal here? On the new disaccharide? Look at the anomeric carbon number 1. Is that a hemiacetal? Sure is. We have OCO. We have a hydroxyl group, and we have hydrogen there. So it's a hemiacetal, okay? That means it can open up. So the right-hand glucose is the only one that can open up, not the left one, because the left one doesn't have a hemiacetal. It has a full acetal. Full acetals cannot open up. Only the hemis can open up. Okay, so maltose is a reducing sugar. It's a disaccharide reducing sugar. So anywhere on that carb, you have a hemiacetal, it's a reducing sugar because it opens up to the aldehyde. Aldehydes are easily oxidized. And this is the acetal, and then this would be the hemiacetal. So maltose, we're going to find our disaccharides will sometimes have a combination of acetals and hemiacetals. So as soon as you see hemiacetal, it opens up to the aldehyde. Aldehyde can be oxidized. Bless you. Now, lactose is made up of galactose and glucose. So this is galactose over here. Notice the carbon number 4 hydroxyl group goes up, not down. And this is glucose over here. Notice the hydroxyl group is going down. Now, lactose is made up of galactose and glucose with a beta. Now, you can, when you do the nomenclature for beta and alpha glycosylic linkages, you can do it like this also, if you want. You don't need the parentheses. I think this is clearer personally, because this to me, I used to be a math major. Using a distributive property, the beta applies to both, and it doesn't. It only applies to the 1, not the 4. Where this is obvious that the beta only applies to the 1. So I prefer this way to do the linkages. You may do it the other way, though, as well. Okay, so if you look at that, it goes down. That's because it formed from the alpha version of that glucose molecule. This goes up. So it's formed from the beta galactose. Okay. There's a hemiacetal on the right side, and it's a reducing sugar. So this is just real easy. Hemiacetal present, yes or no? If it's present, it's a reducing sugar because it opens up to the aldehyde and be oxidized. So that's the second disaccharide you need to know. And really, the only difference between you're already learning the monosaccharide glucose, you're already learning the galactose monosaccharide. Just put them together with the correct linkage, and you have the disaccharide. So it's not like you're learning a new. You're sort of learning a new one, but it's not too bad. All right, and then here's good old sucrose. Good old table sugar. Now, sucrose is a combination of glucose and fructose. And the question becomes, well, gee, is this a reducing sugar? Well, ask yourself, is there a hemiacetal present? Well, here's an OCO. Okay, is there a hydroxyl group on that anomeric carbon there? No. So that means that's not hemiacetal there. Okay, we have another OCO down here. We have OCO. Okay. Is there a hydroxyl group on that anomeric carbon there? No. So this ends up being a acetal at the top, ketal on the bottom. Oh, actually, let me there is an H here, but no H on the bottom one. Okay, Again, there's no hemiacetal there, or hemiketal. Hemiketals can change over to a hemiacetal as well. They're both full-blown acetals and ketals. Hence, it's not a reducing sugar. So that's your tests. Find the hemiacetal. Okay, no hemiacetal, no reducing sugar. All right. Let's look at the linkage now. It's formed from the alpha glucose because the O is going down. Here, down here, the O is going up. So when you attach an anomeric carbon to another anomeric carbon, you have to specify alpha beta. Now, up here, that's not an anomeric carbon. Only carbon number 1 is carbon number 4. So you don't have to specify alpha beta because it only can be one way. If it's an anomeric carbon, it can be alpha or beta. So when we do the linkage, we have to specify. So it goes alpha 1, beta 2. This is carbon number 2. That's the linkage. Now, unfortunately, many textbooks, the structure doesn't look like this. Remember I said earlier that we used to do the anomeric carbon on the right? Well, books, because this is much harder to print, they do the fructose anomeric carbon on the left. So it looks like this. Okay, this is going to be the glucose. So here we have the glucose, and here's the fructose. So this is the anomeric carbon here when you flip it. And that's usually the structure you see in a lot of textbooks. But if we stick to the standardization, having the anomeric carbon on the right, you've got to put them vertically. Okay, I like to be consistent and do it like this. Okay, so we have 6 sugars now. We have 3 monos, 3 dis. Oligosaccharides, they're put together with monosaccharides as well. Now, one of the really important one is raffinose, and that's the one that's real important for babies when they're nursing or when you're bottle feeding babies, because the raffinose oligosaccharide is used as a prebiotic for feeding the baby's gut flora or the gut bacteria. So it's very important that baby gets that prebiotic. Otherwise, those bacteria are going to eat through the baby's intestine, and the baby will end up with leaky gut syndrome. So we have lactose, glucose, fructose. So if you start with sucrose, you're going to add on to carbon number 6 of the glucose and add on a galactose. So this is going down, so it's going to be an alpha 1, 6. Alpha 1, 6 linkage. This is going to be a alpha 1, beta 2 linkage. Going down to the fructose below. Okay, so the age-old question is reducing sugar? Okay, this says no, it's not. That's because there are no hemiacetals present. There's an acetal at the top, acetal in the middle, and a ketal at the bottom. None of them are hemis. The second one is called stachanose, and it basically, you just add another galactose on top of the other galactose. So we have sucrose, raffinose, and we just stick another galactose on top of the raffinose. And like raffinose, it's not a reducing sugar because there's no hemiacetal. Now, this is a really interesting oligosaccharide. The reason why I chose this one is this is the reason why beans cause farts. It's because when you don't soak your beans, you're cooking dry beans, usually pinto beans or black beans, there's an oligosaccharide on the outside of the bean, the dry bean. So if you cook them without soaking them first, what happens is you let that oligosaccharide leach into your wonderful broth of your beans. If you soak them, what you do is you dump the soaking water and start with fresh water, and the oligosaccharides goes down the drain. Of course, you have to think ahead and soak them overnight. There's a quick way to soak them is you can boil them for half an hour and then dump the liquid. It's another way to do it. Some people say it all when you soak it overnight, it makes the outer softer, so your beans are creamier. I always soak mine when I can remember. I cook them in an Instant Pot also. Very quick. Instant Pot pressure cooker. Okay, so anyway, and if you buy Beano, what happens is it kicks off that top galactose. And so you end up with raffinose. And raffinose doesn't cause gas or flatulence. Now, there's another one that is frequently seen as a filler. And it's called inulin. And inulin is made up, instead of having sucrose at the bottom, it's mostly fructose and then glucose at the top. So you're going to have anywhere from as long as it's over 11 or more. Okay. As it's going down, it's an alpha linkage on the top glucose. Okay. And it's hooking up to the carbon number 6 on the fructose. So it's an alpha 1,6 glycosylic linkage. Down here, we're hooking up that's a beta fructose because the OH is going up. And it's hooking up with a beta down here as well. So because this is going up, it's a beta 2. And because this one's also going up, it's a beta 2. Okay, so reactions. Now, these are the same reactions that we did in the last chapter on aldehydes and ketones, only it's a bigger molecule that's got the aldehyde or ketone on it. It's exactly the same reaction. Benedict solution was one with copper. So the copper is being reduced from copper +4 to copper +2. Actually, that's another reaction. Goes from a +2 to a +1. There's a bunch of these reactions that have copper being reduced. If you take Chem 1A, there's a whole lab on copper reducing. It goes from +4 to +2 to +1 to metallic, and it's called a copper cycle. A lot of copper involved. Okay. So the only way copper can go from +2 to +1 if there's something else that's being oxidized. So now we're doing the aldehyde to the acid. And because it's in a basic environment, it's going to end up being the acid salt. That's the essence of a Benedict's reaction. Doesn't matter if it's a plain old aldehyde or it's an aldehyde that comes from a monosaccharide or a disaccharide. And this is a oxidation. Okay, so what does this look like? Let's look at glucose. And we know glucose already is a reducing sugar. So what does the Benedict's reaction look like with glucose? Okay, so we start with, I'm going to draw the open version of glucose. Okay. All right, plus copper +2 in a basic environment. Okay, copper +2 is a really pretty blue. Now, because the aldehyde likes to be oxidized if possible, that means it's going to then reduce the copper +2 to copper +1. So now the acidic version of glucose So we have the glucose opened up to the aldehyde being oxidized. Hence, it's forcing the reduction of copper plus 2 to copper plus 1. That's why they call it a reducing sugar. You need to know this reaction. Now, the reason why I put this copper 2O down there, copper oxide, is because the copper plus 1 binds up with oxygen and it forms this rusty looking color. So, based on the results of these 3 test tubes, this is a reducing sugar, not a reducing sugar, because there's no change. So these, the left and the right one, changed. That means chemical reaction happened because there's a color change, and the reaction involving an oxidizing agent. So that means that oxidizing agent gets reduced. So we have maltose, that's glucose with a hemiacetal, sucrose, okay, glucose, fructose, no hemiacetal, hence it's not a reducing sugar. And then we have lactose, galactose and glucose with the hemiacetal present. So and we can do a very similar reaction using silver. So instead of copper plus 2, we use a silver cation, silver plus 1. And then it gets reduced to silver metal. And this would be the Tollens test. So the open glucose is going to look the same. The oxidized glucose is going to look the same. Just what's different is what's being reduced. And the top one, the Benedict's, the copper is being reduced. The bottom one, the silver is being reduced. Also in a basic environment. Okay, polysaccharides. Polysaccharides are bigger than illegal saccharides. Things like starch, cellulose, those are the 2 most common polysaccharides. Sometimes they're thousands of glucose long. Thousands. When you take cornstarch or wheat starch, these things, the reason why they make your sauces silky is because these long molecules slide against one another. And that ends up being a very nice mouthfeel. Karo corn syrup, also cornstarch. And frequently Karo syrup is added to things like candies and pastries for the same reason. Makes it feel really good in your mouth. And you learn 3 of these. There's starch, which all it is glucose with an alpha 1,4 glycosylic linkage. Now, there's a trick question could be asked. This just shows the middle part of the starch. It doesn't show you the front end or the back end. Well, the back end is going to look like so the question is starch a reducing sugar? What do you think? You're saying no. Okay. And what's using your basis for that? Okay, that's right. These are all full-blown acetals, right? Except for the end. The very end one. Now, remember, this can be 1 to 2,000 glucoses long. One on the very, very end is a glucose with a hemiacetal on it. So technically, this is a reducing sugar. Now, a lot of books will say starch, glycogen, and cellulose, none of those are reducing sugars. But that's not true. Okay, there are two versions of starch. One is called amylose, and the other is called amylpectin. And there's just a branch on carbon number 6. So no branching. And this one we have branching on carbon number 6. And again, it's a reducing sugar because the terminal is a hemiacetal. Okay, glycogen is one carbohydrate we make frequently, and it's stored in our liver and muscle. And when we need energy, we take that glycogen and take it apart and get glucose out of it, and then we burn glucose in the mitochondria through the carbohydrate metabolism cycle, starting with glycolysis. And glycogen and amylpectin look very similar. Glycogen has more branching. And it branches at the same place, carbon number 6. Now, cellulose is also a polysaccharide. And cellulose and starch look exactly the same, except for one difference. And that's the glycosylic linkage is beta rather than alpha. Everything's the same. Glucose, 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 except it's a beta linkage. Our bodies cannot digest cellulose because the linkage is beta and not alpha. We have no problem digesting starch because it's got an alpha 1,4 glycosylic linkage. Cellulose is a beta 1,4 glycosylic linkage. Termites have no problem with cellulose. Cows goats, they have no problem with cellulose, digesting it. Now with us, we don't digest it, but our bacteria like it. That's why sometimes, depending on what we're eating, the bacteria will produce gas, and we end up having gassy problems. Depends on what fiber we're eating. A lot of people used to think that eating beans causes gas because of the cellulose around the bean. Later, they found it was the illegal saccharide that did it. Oh, there are no more slides. Okay, so this is enough for one day. Now, the reactions aren't too bad. The structures are. And that's what gives most people the problems. Because you only have, a few reactions, really. You've got the two tests, the Tollens and the Benedict's test, which is just an oxidation reduction. You have the acetal, hemiacetal reactions. And then you can also reduce the aldehydes and ketones to alcohols. That's it as far as reactions go. So what I want to do starting next week is go over lots of reactions. And there's quite a few worksheets also, extra worksheets there as well. Okay, so that's it for today. I will see you all, well, Thursday people in the lab anyway.